attack explosions in infrastructure, but this happened inside of an apartment building which was located in the corner of a building, and it resulted in progressive collapse. So progressive collapse is one of the topics that I will cover, but we will first start looking at blast loads on buildings, how to do a simple dynamic analysis, and then we'll talk about progressive collapse. As you know, progressive collapse is one member triggering partial or total collapse of a building. A good example is 9/11 event. Right? In 9/11, airplane collided with one of the floors, and that brought down the columns at that floor, and then the intense heat of the fuel reduced the capacity of steel columns, and then columns of that floor started failing, and the story below was not designed to carry 2 stories load, and then it failed, and the story below failed. So it was just a zipper effect. We ended up having progressive collapse. So progressive collapse may be triggered by blast attacks. If you do provide, or if you do attack first-story columns, and columns are responsible for overall strength and stability of the entire building, so you can have a partial or total collapse. Another very notorious example is the Oklahoma City bombing in the US, and this is the Alfred Murray government building, which was attacked by a truck bomb. Over 2,000 kilograms of TNT was placed 2 to 3 meters away from the first-story columns, but as you can see, the entire facade came down, and not only that, but nearby buildings were damaged, and then there was a crater in the ground caused by the explosions. Much research, another example, is the bomb attack on Khobar Towers in Saudi Arabia. And this was a building, in one of the buildings in the complex by the National Oil Company in Dhahran, and it was attacked in 1996, causing 20 casualties. Once again, the front facade came, because there's a reason why I'm emphasizing the fact that the exposed side of the building rather than the whole building is being damaged. And you can see in front of building number 131, there was a crater in the ground caused by the detonation of the explosives. So these are all external attacks, but then there could be attacks from within in the parking garage, and here's an example of the World Trade Center attack in New York City in 1993. So it did cause collapse of the slabs, and it triggered some failure. And elsewhere in the world, in Argentina, there was an attack. This time, it was an attack on a community center, and it brought down masonry walls. So we will look at reinforced concrete columns, reinforced concrete panels, and masonry walls. And we cannot dismiss non-structural elements. And here's an example of an attack in London. This was a bomb attack. It was a truck bomb attack, and it resulted in tremendous failure of glass. And glass fragments, when they fly in supersonic velocities, each fragment can work like a bullet. So it did kill people because of glass failure. And another one is Oslo bombing. There was no structural failure, but glasses of most of the nearby buildings have come down. So when we have a blast threat, by the way, when we talk about earthquakes, we talk about earthquake hazard. Natural hazards are referred to as hazards, but man-made or accidental explosions are referred to as threats. So it's a threat, same as a hazard, which is the action imposed on the infrastructure, generates essentially 3 types of ill effects. First one is shock waves, which is the focus of our presentation today. And then flying debris. I already made reference to projectiles and pieces of concrete, masonry, glass flying into the building, killing people. And then fireball effect, which is outside of our discussion today, effect of fire on buildings is altogether different. And fireball effect is limited to immediate vicinity, not so much infrastructure at some distance. Now, first of all, there are two primary parameters of bomb attack. One of them is charge weight, which defines the size of the bomb. And we use TNT as equivalence of bomb. So when we say 500 kilogram bomb, that means explosives having mass of 500 kilograms equivalent to TNT. Most explosives have the same detonation characteristics as TNT, but there's a conversion factor. Sometimes if they use ammonium, for example, you have to multiply by 1.2 to convert it to TNT. So in structural engineering, when somebody's talking about 200 kilograms of car bomb, they mean to say equivalent TNT. So that's number one parameter. Second parameter is standoff distance. This is the distance between center of explosion and the target. And that distance is very important. So when there is an explosion in front of a building, let's say, the chemicals in the detonation is fired, and then there's tremendous energy that is discharged, and shock wave starts moving towards the building. This shock wave creates incident pressure. Now, as soon as it comes in contact with the building, it reflects from the building. But then another wave of shock wave pressure is coming as well. So there is turbulence in front of the building. This reflection increases the magnitude of the pressure. So we deal with reflected pressure most of the time, especially for front facade, and not incident pressure. So we have to be familiar with these two terms. And then there will be incident pressure causing drag forces from the side walls, from the roof, and even from the back wall with some time delay. Okay? But I mentioned that distance is very important. So here you see effect of about 2,500 kilogram TNT, which is shown in green. And then we have 250 kilogram of TNT shown in red. Horizontal axis show distance. As you can see, as distance increases, then the pressure, incident pressure, comes down very quickly. So distance is very, very important. If you can keep intruders away, then that's number one blast mitigation strategy. This is an investigation of the crowbar building, building number 131. I also have shown the building on the bottom right corner, and left corner shows 80 feet distance explosion, and red implies very severe damage, possible collapse. Yellow indicates very unrepairable damage, and this grayish green indicates possibly repairable damage. So the top left shows 80 feet, but if you move away to 170 feet, then you see damage is decreasing. If you move to 400 feet, damage is limited to repairable damage. So there it was 30 meters, so that makes 90 feet. So it's between the top two figures, but sure enough, it does correlate well with the actual picture. There was very significant damage, unrepairable damage in this case. So with this principal concept, blast being quantified with charge weight and standoff distance, now we will go into analysis and design, which is what structural engineers deal with and civil engineers in general. The same principle that we use in any design applies here. We have to have capacity of members higher than the demand. Demand is the applied force, what's demanded of the structure, and capacity can be force capacity or deformation capacity. As you know, when we deal with extreme events, resisting extreme event is one factor, and dissipation of energy is another factor, which then means to dissipate energy, you have to have inelastic displacements. The area under force displacement relationship is energy consumed, energy dissipated. So ductility becomes important. Nonlinear behavior of materials come to forefront, and that's why we have to talk about force capacity and deformation capacity and compare it with demand. But if you're designing a new blast-resistant building, then of course it's a good practice to minimize demand. Can you do that? Yes, you can. As I already mentioned, if you have the right site selection, if you protect your building against intruders by keeping them at distance, then that's number one strategy. You have to pay attention to the location and selection. And this can also be enhanced by choosing appropriate structural system at the preliminary design stage. Shape of a building matters, for example, okay? And I'd like to go over them very quickly. But proper selection of the layout, location, and structural system is very important. And this can all be achieved through what we usually refer to as soft measures. In other words, hardening is retrofitting. This is the blast terminology. In earthquake engineering, we strengthen buildings. In blast engineering, we harden buildings. It's the same as strengthening buildings. But those are hard measures. We increase column size, we wrap them with FRP, we use different materials to protect them. Those are hardcore engineering measures. And then there are soft measures by keeping intruders out and then by having control or cameras, and this is where monitoring becomes very important. This is where we interact with electrical engineers in our research center. And standoff distance has to be looked at, closest distance. For example, I was involved in the assessment of Canadian Parliament building, and in the Canadian Parliament building, people can drive right by the buildings and they don't want to lose that privilege. They say in a democracy people should visit their parliament, but then they have, because of all these challenges, they have tremendous control. So if you can provide control, people can still come close to the building, but then there's a major street, Wellington Street, in front of the Parliament building, which is about 30 meters away. And if there's a car bomb explosion, we figure that easily one of the towers can come down. So that distance matters, and if you cannot decrease distance for whatever the reason is, then you have to have security control gates. And you then define your perimeter. And as you can see here, this is the security area, and this is the perimeter around. And then you can have different levels of perimeter. One of them could be only limited to people who work in the building. The other one could be limited to visitors, and the other one could be any security measure just to protect the entire perimeter. So there are recommendations for standoff distance. And this table lists them. This is taken from Department of Defense, from US Army. And as you can see, this is indicated as a function of material type. And we will emphasize this. Why? Because blast is a dynamic effect. It's not like applying static load. And this static load would then be reacted by resistance of the building. But at the moment there's dynamics involved, there's inertia force resisting it, right? And when I lecture about this to my students, I give the car example. When you accelerate your car, you lean backward. It's not because somebody is pushing you back, because it's the acceleration of the car, and your mass pushes you in the opposite direction of motion. Here, when there is blast effect, then the mass of the building reacts to it. And this helps you. This is inertia force. And if you have massive structures, as in the case of concrete and masonry, that helps. Obviously, you have to have sufficient reinforcement to increase inelastic deformability, ductility, that's another method. But in terms of mass resistance, concrete is the best material for blast resistance, as opposed to light gauge steel, which is the other extreme. So, based on material used in construction, there are minimum recommended standoff distances, as you can see. Now you can increase standoff distance, many of you have seen, naturally by disguising them, by putting planters to keep intruders away. or these are the scenes that you're all familiar with, bullards placed around